going to say that now their transformation T is onto if every vector W in the space W is the image of some V in the vector space V. Meaning that there's nothing in W outside the column space, because the column space consists of all the vectors that you get when you map V into W. For all, just transform every vector in V. They all go into the column space, and every member of the column space comes from some member of some vector in V. Maybe many vectors in V, because again, any vector in the column space is going to be the sum of a vector in the row, the image of a sum of vector in the row space, and a vector in the null space. So as we've seen, you can have many vectors, infinitely many vectors over here, because there are infinitely many vectors in your null space that map to the same point. Okay. In any case, again, column space consists of all the vectors you get when you map all of V into W, okay? If there's nothing left, that means that every W in W comes from something in V, so the column space is all of W, okay? So I'll say this means the column space is all of W. Okay. Now that wouldn't happen if V and W were both of the same dimension and your null space was non-trivial, because then your column space would be of dimension less than V and so forth. Okay, so you can think about that. T is 1 to 1. We could say it's 1 to 1 if the null space is trivial. Okay, it's 1 to 1 if every vector in W, every vector in the column space, comes from just one vector in V. Okay, so okay, so we're saying every member of the column space comes from exactly one vector in V. Okay, and that's only going to happen if you don't have any non-zero vectors in Vn. Okay, if you have any non-zero vector in Vn, then you're going to be able to add that to whatever the pre-image of this point is, and you'll have at least two vectors that map to the same vector W over here in the column space. And then I'll write it down here. T is an isomorphism if it's 1 to 1 and onto. Now, if it's onto, the column space has to have the same dimension as the row space. If it's 1 to 1, then you don't have a null space. You have just the only thing in the null space is a zero vector. If you put those two facts together and think about it a little bit, since the rank plus a nullity equals the dimension of V, it follows that the dimension of W has to equal the dimension of V. So that if these are an Rn and an Rm, well, then they're both Rn's, same dimension. Means that the matrix that connects them is a square matrix, and that it's invertible. Okay? So I'd say it follows, and I'm not going to go through the details of why, but it follows that n equals m, the dimensions are the same. Also that A is n by n, and it's invertible. That's pretty easy to see why it has to be invertible. It's invertible. You could say it's because the null space is trivial. The null space has dimension 0. And the only way that happens is if your equation AX equals 0 is the result, well, it involves an invertible matrix A, so that X would be the inverse matrix times the 0 vector. Or you could say it even more directly. It's invertible because it doesn't reduce to row of zeros, so that the rank has to equal the dimension of the space, which means a nullity has dimension 0, which means that since a matrix can't reduce to a row of zeros, it's invertible. Okay, well, all these properties come together in this whole idea of linear transformation. And also, we mentioned this very important property, this very important characteristic of some spaces, orthogonality. We're not going to do a huge amount with orthogonality, but it's one of the central concepts in linear algebra, this being a freshman level introductory course. We're not going to be able to get too deep into orthogonality, but we will play around with it a little bit.